and in that we are going to do routing, scheduling, loading. Okay. So these are all a few things that we have already discussed in class. Now today we'll discuss some numericals regarding the production planning and control. So these are the numericals that we'll be discussing. So first of all, we'll be discussing about the Johnson's rule. So we already discussed this, but again we'll go in a brief elaborative way. Second thing that we'll discuss is about priority scheduling rules. So if I want to schedule the production, so what are the priority scheduling rules? So this we have discussed. SPD, that is shortest processing time, earliest due date, critical ratio, first come first serve. So we'll study about a comparative analysis of this. Okay. Then also we'll discuss about some Gantt chart, line balancing, then MRP, that is material requirement procurement, material requirement planning, that we'll discuss, and then master production schedule and lot sizing. So that these are all the 6 types of numericals that you can expect from the this unit. So moving ahead, so first we'll discuss about the Johnson's rule. Now this is about a scheduling. So once we prepare a schedule, first of all we'll decide the route of the production, and then we'll go for a scheduling. Now, the first thing that we'll discuss is sequencing n jobs on 2 machines so as to minimize the make span. So the make span time is the time that required for complete manufacturing of the jobs. Okay. Now that is known as a make span time. So this is the problem in hand. So we have 5 jobs and we have 2 machines. Okay. Now in that problem, what has been given is that 5 jobs must be processed on machine 1 and then machine 2. Find an optimal sequence that makes a total make span. Okay. Now we need to find out a optimal sequence wherein I need to machine the 5 jobs A, B, C, D, E, and these are the times given. That is machining times given in hours for machine 1 and machine 2. Okay. Now moving ahead, what we need to do is we need to go ahead with a Johnson's algorithm. Now, what that Johnson's algorithm says that if I have to process on machine 1 first and then machine 2, then what I need to do, I need to find out first which is having a minimum time. Okay. Now, as you can see here, the minimum time on the machine 1 is observed for job B. Okay. Now, for the job B, the minimum time is observed as 1 hour. So what I'm going to do is on M1 machine, I'll place this as a first job. Okay. Now, similarly, I'll check the next minimum. So the next minimum for the M1 is the job D. Okay. So the next I'll sequence it on this minimum 3 on M1 after B second position. Then the next minimum is 5, and then the next minimum is C, and then the last is E. Okay. But here the what are the optimal sequence that has been given? BDCE. Let us see how it comes, how this comes. So first of all, we need to check that uh, the minimum on A and minimum on the machine 1 and machine B as well. So if it is minimum is on machine B, then I have to schedule it as last. Okay. So this will be scheduled as last. So as it is written, minimum observed in 2 on M2, place this as a last. Okay. Now the minimum this is 3 on M1. Again here this is on 4 on M2, place second from last. Okay. So like that we have to find out. So first of all we have to find out all the minimum times available on this particular job shape. Let us see how we can do. So first of all, minimum of all, what is that minimum of all? It is a 1 hour. So that I'll schedule first. Place B at front. Okay. Now the next minimum. So what I'll do is I'll scratch that out. So this I have scheduled. Okay. So yeah, I'll scratch this out. Okay. Then the next minimum remaining out of remaining minimum is 2. Okay. So the minimum is 2 observed on this. But again, this is on a second machine. If the minimum is observed on second machine, because it is said that first on machine 1, then machine 2. Okay. If the minimum is observed on second machine, what I need to do is I need to place it last on machine 2. Okay. Now that is what being done. It is the B and A. A is scheduled at the last. Okay. Now next step is I'll remove A. So I'll remove A here. Okay. Now the remaining parts are C, D, E. Now out of that, which is minimum? The minimum is observed is this 3. Okay. It is observed on M1. So if it is observed on M1, then what I'll do? I'll put that on the next to D. Okay. Next to B. So this is B, D, and A. So I'll scratch that D because that I already scheduled. Okay. Now remaining is C and E. Now the next minimum that is observed is on E, this machine 2. Okay. So therefore, this is observed on machine 2. So therefore, I'll be placing this at the second last position. Okay. That is E. Okay. And the remaining part is C. So that I'll put it in the center. Okay. So the minimum part, only job remaining, that's C. So this is the final sequence that will come across. That is B, D, C, A. Okay. Now this is how the Johnson's algorithm will work. Now this is the logic of application of Johnson's algorithm. Now this is applicable for only for two machines. We can schedule it for n number of machines. The machines n number of jobs we can schedule it for, but the machine should be only two. Then and then only this is applicable. Okay. Have you understood this? Any doubt in this? If not, we'll move ahead. Okay. So next we'll see n jobs, 3 machines. Okay, so moving ahead, we'll be going for the Gantt chart preparation. So this is a Gantt chart which will give you the max span calculations. So what is the max span calculation? Now this is the max span calculation. Okay. Now we'll start on M1. This uh, B is 1 hour. Okay. D is 3 hours. C is 9 hours. E is 10 hours, and A is 5 hours. Similarly on machine 2, we have B, D, C, E, and A. Now here the machine is remaining idle because the it is getting processed on machine 1. So therefore this machine is remaining idle. Okay. Now let us see how we can start that. Now M1 start at 0. Okay, M1 start, it will finish at 1. Okay. Then at 1 first hour we'll have the D is going to start. Then it will work for 3 hours. Then the finish will be on the 4th hour. Okay. Then the 4th hour, then it will go to this C, 4 to 13, 13 to 23, 23 to 28. Okay. Now the machine 1 will be running for 28 hours. Okay. If I talk about only the machine 1 time, whereas for the machine 2, I'll be requiring much more extra time. Why I require extra time? Let us say once it is finished on machine 1, it will go to machine 2. Okay. Now for this machine 2, the part B requires 6 hours. So 7th hour, the part will be finished. Okay. And here the part D will be finished on 4th hour. So it will start at 7th hour and then it will start at a 15th hour. Okay. So likewise, if you calculate the total manufacturing time for the all the jobs A, B, C, D, E, so this will come out to be 30 minutes and the total idle time that will be for 2 hours. Okay. So that will be for 2 hours. Why? Because so the machine is processing till the time till we receive the components. So therefore it will remain idle for 2 hours. Now this is how we'll calculate the max span of the problem. Okay. So next is let us say if you are going for a tie breaking rules. So let us say there are some ties. Now in that case, how we can apply a tie breaking rule. Okay. Now as you can see, there are 6 jobs on M1 and then M2. Now please note that C and job F. So for C we have this 4 and for F also we have this 4. So this creates a tie. Now we need to apply a tie breaking rule. So what is the tie breaking rule? So again, first of all, we need to find out which is the minimum. Minimum is what? Step 1, find out minimum of the two. Okay. Think there is a typo error. So okay, sorry. So minimum, we have minimum on this as well as this. Okay. So this is a again there is a tie. So there are two ties. There is one here and there is one here. Okay. Now what we have done is that, so since it is observed on machine 2, so we have kept job E at the last at machine 2. Okay, so that will be last, and minimum job 2 that is being observed on machine 1, so it is kept at first. Okay, now next minimum is 3. So next minimum is 3. It is observed on here as well as here. Okay, now job A is observed on this, so this will be scheduled at the last AE. Okay, and then this, uh, because we already scheduled E, so E will be crossed out. Okay, so E and B we have scheduled, so the E and B will be crossed out. Then we'll be talking about this one. The 3 is observed here. Okay, so therefore A will come here. Next minimum is, once we scheduled A, we'll cross that, will remain with C. Now C, for C we have is the 4. The minimum is this 4 and this 4. Okay, now job C at M1 tie with F M2 equal to 4. Okay, now C on M1 and F on M2, so both are the remaining one. Now in that case what we'll do is, since it is on M1, so because we have to process on M1, so what we'll do is we'll process C on M1 and F on M2. So therefore the C will be starting after B and F will go on M2, that is EAF. For M2 will be giving in reverse fashion, and for M1 will be giving in the forward direction. So remaining is the D. So once we schedule this all, only D is the remaining. So that will come in the middle. Okay. So for the tie cases that we can apply these kind of rules, and then we have to find out the solution. In the tie cases, again, if you observe on the both machines, let us say if I get 2 here as well, तो B and C अगर दोनों में tie आता है, then we have to find out on the machine 2 which is having minimum tie. ठीक है, तो machine 2 जिसका minimum रहेगा उसको फिर बाद में शेड्यूल करना है. And the machine 2, machine 1 में अगर machine 2 if it has a longest time, then it will be scheduled first. Okay, so likewise these are the some tie breaking rule that we need to apply in the case of your Johnson's algorithm. Okay, so this is how the Johnson's algorithm is proceeding. Okay. Now proceeding towards, so this we are discuss about n jobs 2 machines. Now we'll be discussing about n jobs 3 machines. Okay, now for this there is some feasibility required when we go for n jobs 3 machines. So what is this feasibility? Now in the feasibility case we have to check these two feasibilities. What are these two feasibilities? So these are the two feasibilities that I need to check: whether the minimum of M1 is maximum of M2 or minimum of M3 is greater than maximum of M2. If any one of these condition is satisfied, then and then only we will be able to proceed with the Johnson's algorithm. Otherwise, we won't be able to produce. We won't be able to go ahead with the Johnson's algorithm. So for that, we have to use some different heuristic algorithms, but this is not a part of your syllabus currently. That we'll discuss in next semester when we are discussing operation research. Okay. Now here, this feasibility rule need to be satisfied. Then and then only we'll be able to proceed ahead with the Johnson's algorithm. Now in this Johnson's algorithm, what we are going to do is we are going to create two fictitious machines. So what are these two fictitious machines? One is G and second is H. Okay. What this G consists of? It is consisting of timing of M1 plus M2, and H is consisting of M2 and M3 combined. Okay. So this will be the sequence that will be followed for making the operations. Okay. Now for that, first of all, let us check the feasibility. What is the feasibility? Minimum of M1. So what is the minimum value of M1? The minimum value of M1 is 3. Then check out what is the maximum of M2. The maximum of M2 is being observed as 4. Okay. Now whether it is satisfying, whether that is it is the greater one, no. So this condition is not satisfied. So let us check the next. On the M3 machine, what is the minimum value? So the minimum value that is being observed is 6. Sorry, there is some typo. So this is 6. Okay. Now this is the 6 minimum, that is the minimum value at M3. So this 6 value is greater than the maximum of M2. So this condition is true. Now if this condition is satisfied, then we can apply the Johnson's algorithm of this. What is this? That is G equal to M1 plus M2 and H equal to M2 plus M3. So this we can apply. So this will be applicable only when this condition is satisfied. Okay. Now once we do that, then again we have to proceed with the similar fashion that we discussed in the earlier. So whatever we discussed for two machines, the same will be applicable for three machines algorithm. Okay. So what we need to do is we need to add the timings for this. Okay. Now let us say G equal to M1 plus M2 and H equal to M2 plus M3. So what you can observe is this is 5 plus 2 7. This is again 6 plus 1 7. 3 plus 4 is 7. Okay. Now here again the timings are getting same. 9 plus 1 10, 4 plus 6 10, 8 plus 2 10. Okay. So everywhere we are getting the same time. Okay. Now all time. So all we are getting time. So minimum overall PQR all time on G. So on S. Okay. So since we are getting that tie on this, okay, so what we'll be doing is we'll be going to use a sequence. Sorry, this table is missing some last value, that is S. Okay, so there is one S value is also there. So this S value is having a total time of for H is 8. Okay, so therefore this will be scheduled at last. Okay, uh, on the machine H. So the sequence that will be following is QPRS. Okay, so again in that, since there is a tie, we can go for PQRS or QPRS or RQPS. So all these things are similar because the timings required on G and H are same. So therefore, the for this kind of machine, so all the sequences are possible. All the sequences are optimal. Like QPRS is written, so RPQS is also feasible. RPQS is also feasible. Then the one more sequence is that PRQ RQP is also feasible. Okay. So what are the three combinations are there? These are all optimal sequences that we can get, which will reduce the max span time or it will reduce the idle time of the machine. Okay. So this is about the Johnson's rule. So this is about the Johnson's rule when we are scheduling the uh, n jobs on the machines. Okay. Now this is when we don't have any priorities or any priorities are not defined. So in that case, I'll be going ahead with the whatever the Johnson's rules are available. Now, in the case when we have a priority scheduling rules, so these are few priority scheduling rules are that is mentioned. So that is FCFS, SPT, EDD, and critical ratio. So the FCFS stands for first come first serve. SPT stands for shortest processing time. EDD is earliest due date, and the next one is the critical ratio. What is critical ratio? So critical ratio is the due date divided by the time that is available for the production. So that is known as a critical ratio. Now these are the few priority rules that we need to apply when we are going for a scheduling. Now for the currently whatever we discussed for the Johnson's algorithm, there were no priority rules. If there were no priority rules, then we'll be going ahead with the what are the things that we have discussed that will be going ahead with the Johnson's algorithm. Now we'll be going at the priority rules. So what is the priority rules? Now this is the problem. 5 jobs arrive at a single machine. Today that is day 0. Apply FCFS, SPT, EDD and critical ratio to find the best sequence, calculate average flow time, average lateness and number of tardy jobs for each rule. Okay. So these are few terms that are being used in any production. So what is this? So the flow time. What is flow time? So the flow time, the formulas are mentioned over here. So the flow time is that. So flow time is completion time minus arrival time. Okay. So completion time since all arrive at day 0. Okay. Lateness completion time minus due date. So usually negative, if the lateness is negative, that means we are doing it early and that's good. Okay. So tardy equal to 1 if you get lateness greater than 0. Okay. And critical ratio is due date minus today upon processing time remaining. So these are the few formulas that will be used when we are going for a priority rules kind of assignments. Okay. So these are the times given. Now the sequence is given. So the first job will be arriving A, 1, 2, 3, 4, 5. So these are the 5 jobs that are coming up. Their processing time is given, their due date is given, and remaining time that has been given. Okay? Same time as that of the production time. Okay? So this is the arrival order. Now arrival order is the same that we'll be using for scheduling, that is known as a FCFS rule, that is first come first serve rule. Okay. Now let us see how we can check out the all the rules. Okay. Now the priority rule, the first one is FCFS, that is first come first serve. Okay. Now the processing time that we are taken. Okay. So for A, B, C, D, E that we are taken, so that is 6, 2, 8, 3, and 5. That is the processing time that has been given. So completion time is 6, due date is 8, lateness is due date minus completion time minus due date, that is minus 2. Is it tardy? No. Tardy means it is the late that is coming up. So if the lateness is positive, then we'll say it is a tardy job. Okay. Now since it is the lateness is negative, lateness is completion time minus due date. So completion time minus due date is the lateness. So that comes out to be minus 2. Okay. So therefore it is early, that is good. Next will be processing B. Okay. So processing B. So processing B, processing time required is 2. So that will be added up and we'll be getting it as a 8. Now the due date for it was 6 days, but we are producing it on the 8th day or 8th hour. So therefore, we are getting the lateness as a positive. So it is late by 2 hours or 2 days, we can say. Okay. So yes, it is starting. Now similarly, once we go ahead with the sequence, so this is 8. So this 8 plus 8 will come out to be 16. Okay. And due date was 15, you'll be getting plus 1. Then again, 16 plus 3, that is 19. It was due date was 9th, but we delivered at the 10 days late. Okay. So again, this 19 plus 5 you will be getting as a 24. Okay. And it was supposed to deliver on the 11th day, but we delivered on 13th day. Okay. So the completion time that will be required, we are, that is the average flow time, that is addition of all 6 plus 8 plus 16 plus 19 plus 24. So that comes out to be 73. So total number of jobs are 5. So that will be your average flow time, that is 73 by 5, that is 14.6 days. Okay. Again, the average lateness is again cumulative addition of the all the lateness. So that will come out to be around 4.8 days. And this one is tardy jobs. How many tardy jobs are there? So there are around 4 out of 5 jobs are being late. Okay. Now, if I go ahead with this rule, this is not an optimal rule for the scheduling. Why? Because I'm getting almost all the jobs being delayed. So these jobs are being delayed. Out of 5 jobs, 4 jobs are being delayed. So therefore, this is not an efficient way to schedule any jobs. Okay. So the FCFS fails in this case. FCFS for first come first serve is going to fail in this case. Okay. So that is the average tardiness for the FCFS rule. Okay. Now moving ahead, second thing that we'll be discussing is about shortest processing time. Okay. So the shortest processing time, what is the shortest processing time? So the job which is having the lowest amount of time, that will be scheduling first. Okay. So as per the sequence that is being scheduled, so the lowest of all is being observed on B. So therefore B will be scheduled first. That is the sequence B, D, E, A, C. Okay. Now it is again similar what the things that we discussed in the first one, that is FCFS, first come first serve. The same will be done here. It will be the 2, the due date was 6 and the lateness was 2 minus 6, that is minus 4. So again 5 minus 4, 5 minus 9, that will get minus 4. 10 minus 1 will be 11, you will be getting minus 1. Okay. So it will be 2 plus 3 will be coming at 5. 5 plus 5, this will be coming as 10. 10 plus 6, that will be coming as 16. 16 plus 8, that will be coming as 24. Okay. And the completion time, that will come out to be 57. Okay. And the lateness, we will be getting only 2 tardy jobs, whereas in the earlier case, we are getting 4 tardy jobs. Okay. So this is the time that we'll be getting is 11.4 days. That is the average flow time. And tardy jobs have been reduced to 2 out of 5. Now the SPT is going to minimize the average flow time and average waiting time. And this is base rule when your objective is that we need to achieve the maximum amount of production, or we want to get the maximum utilization of the factory. Now, in that case, I can use the SPT rule. Okay, the shortest processing time, I'll be using the first. But again, sometimes what we get is that some products will have a due date early. Now, in that case, the demand for that particular product may be larger. So for that case, we need to go ahead with the earliest due date rule. Okay. So likewise, you can see here. Okay. So the B job is having due date of 6 days, but we are completed on second day. So it will be in the inventory for 4 days. Similar for this D job also will have 4 days inventory. We have to keep the D jobs waited till we get the demand for that, and this can cause a inventory pile up. So inventory आपका ज़्यादा रहेगा in that case. So therefore, sometimes the SPT role, even though it is giving an optimal average flow time, it causes damage somewhere else. The damage is happening in the inventory. So the inventory will be increasing. So therefore, we need to avoid sometimes the SPT rule as well. But if your sole objective is increase throughput speed or the production speed, yes, then we have to go ahead with the SPT rule. Okay. But usually in the industry, we don't have only one sole objective. We have multiple objectives to be tackled on. Okay. Now the next one is the earliest due date. So the earliest due date, which is having the due date earliest, accordingly it will be scheduled. Okay. So likewise, now here the sequence have been changed. Now what is the sequence have been changed? Now the B, A, D, E, C. Okay. So according to due date, we have scheduled. Okay. So this is the actual sequence that will be obtaining. Okay. Now the completion time that will be getting here is this. So according to due date, we have scheduled. Okay. Now if you can check that, so with this, we are getting, this is just on time, A. Okay. And there are 3 jobs which are being late, or 3 jobs are tardy. Okay. But again, this is going to reduce the maximum lateness. So lateness, if I want to reduce, like we want to match with the supply and demand. So if you want to keep up pace with the supply and demand ratio, so we need to go ahead with the earliest due date rule. Okay. So FCFS rule that we discussed. So it is not serving any kind of purpose. So it only the process within the sequence. Once the job comes, then we'll be processing. Then next we'll be following is the SPT rule. So SPT rule is for optimizing the factory, and EDD rule is for maximum lateness. So if you have maximum lateness, minimize the maximum lateness. So whatever the lateness that we are getting, that will be minimized. Okay. So the average flow time here in this case is 12.2. So the first FCFS provided around 14 days. SPT provided 11.2, 11.5 something, and this provided 12.2 days. Okay. Now these are the few rules that are discussed. Now the next one is critical ratio. So this is very important. The most of the times, usually in the industry, this is being followed. The critical ratio. Okay. So the critical ratio, usually what we are going to do is we are going to find out the due date minus today and what is the remaining time. Okay. So A, B, C, D, E have been given. Okay. Now the critical ratio has been calculated. Okay. So critical ratio is 8, due date is 8 divided by remaining time. So remaining time is 1.33. So this is 3, 1.883, 2.20. Okay. So now, which is to be scheduled first? Okay. Now, what we need to do is we need to go ahead with the lowest critical ratio first. So which is the lowest? So the lowest critical ratio is having A. Then we have scheduled E. Okay. Then we are going for B, D, C. Last due to large CR. Why? Because so for the due date, again, when we are getting some ties, we need to check that the interpretations as well. Okay. So what is the interpretation here? So because it is on track, it is having the due date at the last. So we can process this as a last. Okay. So therefore, also we need to check out the due date rule as well. Okay. Now, according to that, we are going to schedule this. Okay. So the critical ratio priority, we need to check that things and then we have to schedule. Okay. So the sequence that will come out with the critical ratio is A, E, B, D, C. Okay. So in the critical ratio, we also need to check about the due date as well. Okay. We have to check the EDD and critical ratio combined. So these things we need to check in the when we are scheduling in the object. Okay. So this is how the priority rules will work out. This is how the priority rules will work out. And once we are sequencing with this, okay, then we are going to make the Gantt chart. Okay. So Gantt chart that we have discussed already. So Gantt chart just gives you overview where in which machine, which kind of work is going on, which worker is working on, and how the times are being utilized. So in a factory, we have 8 hours of shift, and we need to utilize the maximum 8 hours. Okay, so 8 hours comes out to be 480 minutes in a 8 hour. So these all 8 hours we need to utilize in a factory. So that is being understood through Gantt chart. Okay, that will tell you the utilization in an overview. Okay, so this is how the Gantt chart is being made. Okay, so this is the sequence. Three jobs are to be processed on three machines. Each job has a fixed routing. Draw the Gantt chart and find the make span, machine utilizes, and idle time. Okay. So each job has a fixed routing. What is the routing that has been given? So it is job 1, 2, 3. So it will follow the same sequence. It will process from 1 to 3 as it is. Okay. So first 3 hours, since the J1 is being processed, so the machine 2 will remain idle here. Okay. So the sequence is same. J1, 2, 3 will be produced on the same. Okay. So this is the time that is being utilized. So for machine 1, we don't have any idle time because once the job 1 is completed, job 2 will come, job 3 will come. So okay, so that is 3. Then we have this 4, 2. Okay, then the machine 2, first 3 hours it will remain idle, and after that we'll have job 1. So job 1 will be requiring 2 hours. Okay, and after that again it will remain idle. Why? Because the job 2 is not yet to be finished. So job 2 is yet to be finished, then it will remain idle, then it will go to job 2 and then the job 3. So there is no idle time because job 3 is already processed and it is the waiting period for job 3. Okay. Similar kind of thing is happening on the machine 3 as well. Okay. Now this is how a Gantt chart is being prepared. Okay. Now, this will give you the best understanding of how the machine is being utilized and when the machine is being idle. The same thing we can apply for your workers as well. Okay? You can create a Gantt chart for the workers as well, how the workers are being utilized. So these all things we can include in the Gantt chart. Okay. Now you can find out the utilization time like this. So the utilization time that is being available time and divided by the actual time. Okay, what is the available time? So the machine was one was available for 18 hours and we have used it for only 9 hours. Okay. So it is idle for 0 hours. So we have 50% utilization that is being done. Okay. So for machine 2, we have utilized for 10 hours and it is remaining 3 hours idle. So that is the 55% utilized. Again for machine 3, the actual work that is being utilized only for 9 hours. So this is also utilized by 50% only. So 3 hours is being idle and it is being idle for 7 hours. Okay. So total the hours that is being wasted are this. So we have utilized 28 hours and 17 hours are being wasted. Okay. So the overall equipment utilization that is comes out to be around 51.9%. Okay. So this is the machine utilization and the efficiency chart that usually you will obtain once we do the analysis for from the Gantt chart. So this is known as a overall equipment efficiency. Okay. Now this is about the Gantt chart. Okay. So any doubt up to this? So we discussed about Johnson's algorithm. Then we discussed about the scheduling times, earliest due date, shortest processing time. Then we discussed about a critical ratio, okay, FCFS, okay. Then we also discussed about the Gantt chart. Any doubt in this? ठीक है. Okay. So we'll moving towards the next, that is a line balancing, and then we'll stop. Okay, we'll go ahead with the line balancing problem. So this is again a largest candidate rule, RPW and efficiency calculation. Okay. Now in the line balancing, what we need to do is, so this is usually done in the case of an assembly line. Okay. So in the assembly line, we have multiple activities to be done. Okay. For example, let us say we are doing an assembly of a car. Okay. So for car, there are multiple activities. So the multiple activities can be, let us say task A. Task A, what I'll be requiring is the engine. Okay. So the engine assembly. Then second, I'll be going for a frame assembly. Okay. So on the frame, the engine will be placed. Okay. Now, if the engine is not available, the task B won't be executed. Okay. So that will be the immediate predecessors will be required. Okay. Then the C is again transmission. Let us say it is a transmission box. Okay. So the for transmission box, I need an engine assembly. So the engine assembly need to be there. Then and then only I'll be able to fix up the transmission box. Okay. So the that is what the immediate predecessors are being mentioned. Okay. Now this is the frame, that is where the engine is being placed. Frame, or you can call it frame. Then let us say that task D is chassis. Okay. Now this is the chassis on which the frame, transmission and the engine are going to be placed. Okay. Now for that, the both B and C to be completed, then and then only the chassis will come. Okay. So chassis will come, and then all this for that chassis, all these first three to be completed, then and then only the chassis can be assembled. Okay. Now similarly, the next one is E. Now for E, let us say this is the body of the vehicle. Okay. Let us say that is the body of the vehicle or the body structure of the vehicle. Now for the body to be in place, I require a frame or chassis to be in place. Okay. So therefore, the body, for placing the body, I'll be requiring B and C to be completed. So likewise, this is the sequence of operation when we are going in the assembly. Okay. So, and these are the time required, usually the time that we find out using the work study and method study techniques that we discussed in unit 1. Okay. Now, these times are given and we need to balance the assembly. So what are the assembly balancing we have to do? Now the data is given. So an assembly line operates on 8 hours per day. Demand is 120 units per day, and 8 tasks with precedence constraints have been given. Balance using the LCR method. So LCR is largest candidate rule method. Okay. So this method we have to follow. Okay. But when we are going at this method, this predecessors need to be completed. So we won't be able to start if the predecessor is not complete. Okay. For example, if I want to start E, both B and C to be completed. If I want to start F, C is to be completed. Okay. And if I want to start G or H, the D and E to be completed, and F and G is to be completed. So the predecessors need to be completed before starting any kind of operations. Okay. So this is how we'll calculate the cycle time and the workstations required. Okay. Now these are the calculations. The first calculation is available production time. So 8 hours a day, we are having around a 480 minutes per day. Okay. So what is the cycle time available for one assembly? So that is 480 divided by 120. Now this cycle time comes out to be 4 minutes per unit. So in a unit, I need to assemble all the operations to be done in a 4 minutes. Okay. Next, what we can do is we have to check whether C is greater than the T max. Whether C is greater than T max. Yes, if the cycle time is greater than T max. No. So in that case, what is the T max? The T max will be observed as maximum time out of this maximum time in this all operations. So the maximum time is 7 minutes, or that we usually call it as a bottleneck station. So this is a bottleneck, that is the maximum time required is a 7 minutes. Okay. And whereas we observe that cycle time is 4 minutes. Okay. Now, since the C is not greater than T max, we won't be able to do it in single workstation. Okay. Now, what can be done? Now here, since we require the C to be almost equal to the 7 minutes. So 7 minutes is, so that we need to check out how much things we can do. Okay. Now here what we can do is, so we max output that we can get is 480 by 7. That is around 68 units per day. But our target is how much? Your target is 120 units per day. Okay. Now we need to find out the minimum number of workstations. So minimum workstations, how will you find out? So we'll calculate summation of T divided by the maximum C. Okay, that is the 7 minutes. So that will come out to be 34 by 7. So that is 4.586. That will be coming out to be 5 workstation. Okay. So I'll be requiring 5 workstation that are to be done. So the maximum feasible output from this 5 workstation. So in a single workstation, I can get it around 68. Okay. So I can utilize the workstation effectively. If I use effectively, I'll be getting 68 into 5. That many components in a day. Okay. But since there are some unassignable causes, you won't be able to do it all the 68 units on one workstation. Okay. So therefore, we have to assign them according to the number of workstations. Okay. Now, going ahead, we'll be going to use the LCR rule. Okay. So here what we are going to do, so we are going to assign some workstations. So there are 4 workstations that we are going to assign over 5. So this workstation, what we are going to do is we are going to assign the multiple tasks on the workstations. Okay. So the workstation, like the things that will be requiring, let us say engine, transmission and frame. So they can be combined in one workstation. So that assembly will be done in one workstation. Parallelly, we'll do the second assembly in the second workstation, and similarly, we'll be going to the next workstation accordingly. Okay. So therefore, we'll assign the task according to the precedence. Okay. So here, what we have to do is we have to assign the task with largest time first and without exceeding C equal to 7 minutes or violating the precedence. तो उसमें आपको precedence करना ही है. ठीक है. So let us go ahead with the workstation 1. तो workstation 1, what are the eligible tasks? तो सबसे पहले the eligible one is A, because it is not having any precedence. Okay. So we'll be taking A as a first component. Then task time that will be required is 3 minutes. So cumulative that we have used in workstation, that is 3 minutes, and we have around 4 minutes left. Okay. Now once we assign A, we are remaining with the other activities. Okay. So we have assigned activity A on WS1. Okay. First वाले पे assign किया. Now the time remaining is what? So the maximum cycle time for the workstation is 7 minutes. So we cannot go ahead beyond 7 minutes. Okay. So therefore, now we have the remaining tasks are B and C. Okay. Now out of this, if I assign B, the total time will be around 8 minutes. That is 3 plus 5. So therefore, B is not a eligible candidate for workstation 1. The C is eligible. That is 3 plus 4. I can assign the 3 plus 4. That will come out to be 7. Now that is what being done. That is the largest eligible. And we have 0 minutes that are to be left. So total work session time that we have utilized, all 7 minutes we have utilized. Okay. So this is how the calculations will be done. Now moving ahead, we are done A and C. Now we are remaining with a B. Okay. Now we will be moving towards workstation 2. So workstation 2, what we have available. So A is done, C is done. Okay. A is done, C is done. Now we available with a B and D, E, F. The remaining parts are B, D, E, F, G, H. Okay. Now let us say which of this we can schedule. Now since A and C are completed, we can schedule B. Okay. We can schedule B in the workstation. Then we can schedule F as well. Okay. We cannot schedule E because we require B to be completed, and D also cannot be scheduled in the same workstation because B need to be completed. Okay. So we have options of only B and F in the workstation 2. Okay. So let us say we are going for again largest candidate rule. So largest candidate, what we are going to do, we are going to assign the activity F in the workstation 2. Okay. Now once we assign F, the F is assigned. So likewise, we will be going ahead with the all workstation. So that is what the line balancing that is being known as. So line balancing, if you can check. So here, the workstation 1 is completely utilized. We don't have any time being left. Here, the 2 minutes are being left. Workstation 4, we have 1 minute left. Okay. So uh, this is the how we can schedule. This is how we can schedule the all the jobs that are being available in the assembly. Okay, this is known as a line balancing problem. Okay, this is how the largest candidate rule is being applied. Okay. So we have to find out the actual time. Okay, so you have to follow these steps. So these are all 6 steps to be followed, and then we are going to find out the LCR rule. Through that we will be assigning the problem. So what is the assignments that is being done? WS1, we will be doing A and C. Workstation 2 only F. Workstation 3 B plus E. Workstation 4 D. Workstation 5 G plus H. According to the largest time first or the largest candidate rule. Okay. So this is how the assignment is being done. Okay. Then efficiency and balance delay that is being observed. So what is the workstation assignments? Okay. So the total time for the total task time that comes out to be 34 minutes. Cycle time is 7 minutes. So total time is available 30 minutes. Idle time n into c summation t. So it will be 34 minus 34, that is 1 minute. Only workstation 4 has a 1 minute delay, and the balance delays, it is n into c minus summation of t upon n into c. Okay. So this comes out to be only 2.86%. So that is the only balance delay we have. So the line is completely efficient. So line is a very efficient. We have only a delay of around balance delay is around 2% or 3% we can say. So the line is 97% efficient. Okay. So this is how the calculations have been done on the